Hello everyone. So welcome to the second session on partial differential equations. So in this session we will discuss about a method which is called as a variable separable method, and it's very helpful whenever you have whenever you have a linear differential equation. So what does the method says? So whenever you have a partial differential equation which is linear, I mean it's not necessary only for linear, for non-linear also it might work, but we are not sure about the non-linearity, but for the linearity this usually works. So what does the method says is, you assume that, suppose you have a partial differential equation. So in this one I have written u with respect to x plus u with respect to y is equal to something. So where x and y are what? Independent variable, and my u is dependent variable. So what we assume is, we assume that the solution u, with the solution which is u, which is the function of x and y, can be written as the product of two functions, which is nothing but it in one function involves only the terms of x, into one function involves only the products of y. That means we can separate x and y. I mean, before that one should know what do you mean by a solution. So when you call something to be a solution of a partial differential equation, so suppose if you have a partial differential equation, so f of, suppose x and y are my independent variables, suppose u is my dependent variable. So suppose if you have, these are the partial derivatives. So if you have a partial differential equation, so what is the left hand side? It's a function. That means it's a relation involving independent variable and dependent variable and its derivatives. So if you have a partial differential equation, then when I will say that u is a solution of above equation, when I will say u is a solution, if you substitute your u in the above equation, it should satisfy that differential equation. In that case we say that u is the solution, obviously in some given domain. But in that case we say that the u is the solution. Now suppose if I give you suppose del by u by del by x into del by u by del by y is equal to u. Now this is a non-linear differential equation. You can see my previous session and we will realize that this is not a linear differential equation, because the coefficient of highest order contains the, so highest order is 1 and the coefficient contains the partial derivative. So therefore it's not a linear, it's a non-linear differential equation. And one can see that if I take u, which is u of xy, if I take u to be x plus a into y plus b, where a and b are what? Where a and b are constants. Then one can see that of my u is a solution of this. Why? Because what is del by u by del by x? It is y plus b. What is del by u by del by y? It is x plus a. And when I take the product I get nothing but u. So therefore u is a solution. And you can see that, I mean you can write this is nothing but, this is some function of x, which is nothing but x plus a into some function of y. So this is a variable separable solution. That means I am able to separate my solution. So whenever you have a solution of such type where you can separate the variables, that means you can write the solution into product of two functions, then we say that it's a variable separable. Not all, I mean, like if I take another example, suppose if I take second example as del by u by del by x, I mean x into del by u by del by x plus y into del by u by del by y is equal to del by u by del by y square. So as one can say that this is a non-linear differential equation, because the degree of the highest derivative is not 1. So this is a non-linear differential equation. So one can see that u is nothing but, if I take ax plus y the whole square upon 2, where a and b are what? Constants. So if I take this as my u, so one can see that it satisfies this differential equation and therefore u is a solution. But you can see that you cannot write this as some function of x into some function of y, because the first term is a square x square plus 2a xy plus y square plus b whole divided by 2. So you cannot write something in terms of x into something in terms of y. So not all solutions can be written in this way, but yeah, many times, as I told you earlier, whenever you have a linear differential equation, you just give a shot whether, if you assume it to be a variable separable, then can we find u. So yes, for linearity it works. So that's one thing. Now let's see some examples. So I'll be taking 4 examples, or let's see 3 or 4, and then I mean, I hope the method will be clear to you. So if I take this as a first example, as you can see, it's a first order because the degree highest order is 1. It's a linear. Make sure you convince yourself. And because of the right hand side, it's a, yeah, so no, it's a homogeneous as well. Okay, because all the terms either contains dependent variable or its derivative. So it's a linear, homogeneous, first order differential equation. Okay, now assume that suppose u is the solution. Suppose I can write u as a product of x and y of y, some function of x and some function of y. So now since u is a solution, so when I find u with respect to x and u with respect to y, and if I substitute, that means what? It will satisfy the above differential equation. So what is u with respect to x? It is nothing but y of y will be as it is into this with respect to x means my ordinary derivative, means d capital X upon d small x. Okay, this is nothing but y into, I am not writing y of y again and again, dx upon dx. So this is what it means. Okay, so I will be using this notation or y into x dash. This notation I will be using many times. Y into x dash. What does this mean? This is nothing but y of y into x dash of x. Okay, what is u with respect to y? Again, since this is a function of x, this will be as it is into y dash of y. So now since u is a solution, it will satisfy equation 1. This is my equation 1. So what will I get? What do I get is x dash into y plus y dash into x equal to x plus y into xy. Make sure my small x and small y are independent variables. My capital X and capital Y, they are the functions of x and y respectively. So don't get confused with the notations. Okay, so when I divide this by x and y, xy, what do I get is x dash upon x plus y dash upon y is equal to x plus y. So this is what do I have, and then one can rearrange and one can observe that this is nothing but if I take x dash upon x minus x equal to y minus y dash upon y. You take small x on left hand side and y dash upon y equal to on right hand side. So what is your left hand side? Your left hand side is everything is in terms of x. Your right hand side is everything in terms of y, and I am saying they are equal. So obviously this thing should be my constant k, because if this is a function of x and this is a function of y and I am saying they are equal, means what? They should not contain the variable, otherwise they won't be equal. So if I am saying that they are equal, they have to be constant. So let's solve them one by one. So what do I have is, so this is nothing but, so x dash upon x minus x is equal to k, and y minus y dash upon y is equal to k. Now these are nothing but my first order linear differential equations and I can solve them easily. So this is nothing but, if I rewrite this is nothing but x dash upon x equal to k plus x. This is y dash upon y, I am taking this on the left side, and this is nothing but y minus k. And now if you simply do the integration, so this is nothing but integration of dx upon x is equal to integration of k plus x dx, integration of dy upon y, integration of y minus k dy. And this is simple integration. This is nothing but ln of mod x equal to kx plus x square by 2 plus c1, ln of y is equal to y square by 2 minus ky plus c2. So if I take exponential on both sides, e raised to kx plus x square by 2 plus c1, again exponential on both sides, e raised to y square by 2 minus ky plus c2. So therefore I got my x and y. So what is my u? My u is nothing but x into y, which is nothing but e raised to kx plus x square by 2 plus c1 plus y square by 2 minus ky plus c2. So if I call e raised to c1 plus c2 as c, so another constant c, so this is nothing but e raised to x square by 2 plus y square by 2 plus k into x minus y. So this is what the solution is. If you are not sure, then you can find ux, you can find uy, and if you substitute in the given partial differential equation, then it will satisfy. So this is how you can use variable separable method to find the solution of a given linear homogeneous partial differential equation. Okay, let's go for the second example. So if I take second example as y square ux minus x square uy is equal to 0. So as one can see, this is first order linear homogeneous partial differential equation. Again you do the same thing. Suppose my u, which is nothing but solution of the given differential equation, can be written as product of two function, where capital X is a function of x, capital Y is a function of y. So this implies your ux is nothing but x dash into y, your uy is nothing but x into y dash, and if I plug in over here, I get y square x dash y equal to x square x y dash, and if I take everything, all terms of x on one side and all terms of y on one side, so this is what I have. So I have x dash upon x square x equal to y dash upon y sorry. And now as you can see, my left side is a function of x, my right side is a function of y, and they are equal. That means they should not contain the variable, they have to be constant, otherwise they won't be equal. So again, if you solve one by one, so what do I have? I have x dash upon x square x equal to k, and y dash upon y square y equal to k. So what does this imply? Your x dash upon x equal to kx square, your y dash upon y equal to ky square. So if you integrate, integration of dx upon x is equal to integration kx square dx, and integration y dash dy upon y integration ky square dy. And now this is simple integration. This is nothing but ln of mod x equal to kx cube by 3 plus c1, ln of mod y is equal to ky cube by 3 plus c2. So what is my x? Our x is nothing but e raised to kx cube by 3 plus c1. Our y is e raised to ky cube by 3 plus c2. And what is our u? Our u is nothing but product of x and y. So what is our u? Our u is nothing but x into y, which is nothing but e raised to kx cube by 3 plus c1 plus ky cube by 3 plus c2. And if I call e raised to c1 plus c2 as c, then what will I get? This is nothing but c into e raised to k x cube plus y cube. So e raised to k by 3 into x cube plus y cube. If you want to remove k by 3, you call k by 3 as some another constant, say m. Then it will be c into e raised to m x cube plus y cube. And these are called as a general solution. If you, there's something called as a particular solution as well. I hope you have seen this while studying ordinary differential equations. So since the solution involves arbitrary constant c, therefore these are general solution. If I have some particular solution, of if I have some particular value of c, then I will call it as a particular solution. Okay, that was my second example. Let's go for the third example. So my third example is my u with respect to x is nothing but 2 times u with respect to y plus u. So this is my third example. So again do the same thing. So now I'll be doing bit fast. So make sure you understand the steps. If you have any doubt, you can ask me in the comment section, no doubt. So you do the same thing. My u is a function of x and y. So my u with respect to x is x dash. My u with respect to y is xy dash. And this becomes x dash y equal to 2xy dash plus xy. So this is if I divide by xy on both sides, I get x dash upon x equal to 2y dash upon y plus 1. I'm simply dividing by xy on both sides. And now again this is a function of x, this is a function of y, so it has to be constant. So let me call that constant as k. So what do I have? I have x dash upon x equal to k. I have 2y dash upon y plus 1 equal to k. So this is nothing but integration of dx upon x equal to integration of k dx. Integration 2 dy upon y is equal to integration k minus 1 dy. This is ln of mod x equal to kx plus c. This is 2 ln of mod y k minus 1 y. Let me call constants as c1 and c2. So and if you solve this further, so what is my x? X is nothing but e raised to kx plus c1. My y if I divide by y, so nothing but e raised to k minus 1y by 2 plus c2 by 2. Okay, and what is my u? So ultimately my u is nothing but which is product of x and y. So if I call again e, if I take the product e raised to kx plus c1 plus k minus 1y by 2 plus c2 by 2. So if I take e raised to c1 plus c2 by 2 as some another constant c, what I'll be left with c into e raised to kx plus k minus 1y by 2. So this is what the solution is. So as you can see, this is a very good method. It helps us to get the solutions very easily. And now let me take one last example and then we will stop. So for last I'll be skipping some step. I am doing this just to give you an overview idea. Okay, so let's take the next example. 2x ux minus 3y uy is equal to 0. So again same thing, my u is what? xy. So what is my ux? It is nothing but x dash y. My uy is nothing but xy dash. So this is what I have. So if I substitute over here, I have 2x x dash y is equal to 3y xy dash. So this implies 2x x dash upon x equal to 3y y dash upon y. And again the same logic, my left side is a function of x, my right side is a function of y, and they are equal. Therefore they have to be some constant k, and if you solve them one by one, so I have 2x x dash upon x equal to k, 3y y dash upon y equal to k. And now again this is easy, integration of dx upon x is equal to nothing but integration 1 by 2 k by x dx, and this is nothing but integration of dy upon y is equal to 1 by 3 integration k by y dy. And so this is nothing but ln of mod x equal to 1 by 2 ln of small x. You can take ln of c1 so that the ln will go away. Ln of mod y equal to 1 by 3 ln of y, plus you can take ln of c2, because so that the log will go away. And when you try to simplify this, so what is my x? So this my x will be x raised to 1 by 2 c1, my y will be y raised to 1 by 3 c2. So what is my u? It is the product. So if I call c1 into c2 as c, so my final answer is x raised to k by 2 into y raised to k by 3. So all this are the general solutions for the given partial differential equation. But if suppose sometimes some initial conditions are given to you, then you can use those initial conditions to find the particular solution. So let me just state one last thing. So suppose if you have 4ux plus uy is equal to 3 times u, and u of 0y is equal to e raised to minus 5y. So this is a partial differential, first order linear homogeneous partial differential equation with some initial condition. Some condition is given to you, and now if you try to find the solution of this differential equation, your u will come out to be some c into e raised to kx by 4 plus 3 minus k into y. You try to solve this, you should get this as an answer. And now you use this initial condition to find the value of c and k. So what is given to me? E raised to minus 5y is equal to u of 0 comma y, which is c into e raised to 0 is 1, I mean not 0, e raised to 0 plus 3 minus k into y. So what do I have? E raised to minus 5y. And now if I equate on both sides, the coefficient of c is 1, so my c is 1, my 3 minus k is minus 5, so therefore my k is nothing but 8. So therefore what is my u of xy? It is e raised to c is 1, k is 8. So this is the solution which will satisfy the differential equation as well as it will satisfy the given initial condition. So this is called as a particular solution of the given differential equation. So I hope the method is clear. If you want, for practice sake, you can take some few examples. Let's take this as a homework problems. 3u with respect to x plus 2u with respect to y equal to 0, and take the initial condition as 4 e raised to minus x. This is one thing, and the answer for this is your u of xy will come out to be 4 e raised to minus 1 by 2, and this is the solution of that first question. And second one, you can take y cube ux plus x square uy is equal to 0, and for this the general solution is so these are the two examples with the solutions given. First one is the particular solution, second is the general solution. So you can work it out. If you have any doubt, you can ask me in the comment section. So I hope the method is clear. Thank you and have a nice day.